Okay, let's start a new chapter, chapter 16, another mitigation option for greenhouse gases by enhancing carbon sinks in natural and working lands. Usually we talk about deforestation, urbanization, conversion to agriculture as human impacts, whereas calling them working lands actually reminds us that we are using them for our own existence. So it's just a matter of not doing that in a way that basically degrades the environment. Enhancing carbon sinks also means protecting soil, protecting biodiversity, habitats, reducing emissions, etc. What are the options there? Fertilizer use, deforestation, etc. Right? So we look at natural and working lands in the terrestrial carbon cycle. We haven't done explicitly carbon cycle in this course, and we will not go into lots of details here either. But we will touch on it as much as needed for making this chapter complete. Soils, organic matter, and greenhouse gas dynamics. Soils are full of microbes, carbon, organic and inorganic carbon, organic matter that is also, and there is production of carbon dioxide because hydrocarbons generated by plants and shrubs and so on are being converted into respired into carbon dioxide. There is also potential methane production in wetlands because of anaerobic digestion and so on. The role of plants in carbon storage and greenhouse gas emissions. Obviously, terrestrial carbon cycle has to touch on that. There is recently been a lot of news about planting 1 trillion trees as a solution to climate change, and as you've probably seen, there is lots of controversy about it, basically about whether mature forests continue to take up carbon, and when there is wildfire and they belch all the carbon back, then what is actually accomplished, and so on and so forth. Emissions reduction via management. What are the management options? So it's not just about enhancing sinks, but also reducing emissions. Soil carbon recovery and sequestration. What can be done to enhance carbon sequestration in the soils? So let's jump right into one carbon cycle, terrestrial carbon cycle picture that shows fluxes, where the red arrows are showing an enhancement of the quantity being shown by diversity of trees, and the blue arrow is enhancement because of the forest age. So in this case it could mean enhancement of fluxes or enhancement of the carbon stock. So we are looking at reservoirs. So like tree above ground carbon here is how much carbon is locked up in trees, because that's also an indication of how much of that could be released when there is wildfire, for example. Okay, so 57.4 megagrams carbon per hectare, with some uncertainty there of almost 10%. Soils are heterogeneous. Vegetation and shrubs and ecosystems, biomes, whatever you want to call them, are very heterogeneous. So there are always uncertainties and difficulties in estimating these at global scales or even regional scales. Lots of the data tends to be local, but we'll see that remote sensing allows us to make estimates at certain global scales as well. So here is above ground carbon flux in megagrams carbon per hectare per year. So that's 1.7 plus minus 0.1, and RS here is the root carbon and root flux, so flux coming out of here, 2.6, and shrubs, a small quantity there. This is the deadwood carbon, and this is the coarse deadwood. So this is fluxes here, you can see. So the solid boxes are reservoirs, and there are fluxes here in deadwood carbon pool as well. sorry, that's the stock as well. Okay, so anything with the -C is carbon stock, and anything with F is a flux. Okay, make sure I said it right. So there is our soil organic carbon, which we are going to worry about a lot in this chapter. 61 megagrams carbon per hectare with some 10% uncertainty as well. And roots which produce the carbohydrates and leave them into the soil to feed all the biodiversity of microbes in the soil. It's said that 1 teaspoon of soil has more microbes in number than all the human beings on the planet. That's many billion microbes in a teaspoon of soil. So soil is very rich in microbe biodiversity, so obviously has to be protected, but because each one has its own role to play, symbiotic roles with the trees and so on and so forth. Okay, so looking at below ground carbon total, that's almost 81 megagrams carbon, ground carbon, above ground carbon, and so that's surface, and that's the total, almost 150 megagrams carbon per hectare. Okay, so keep those numbers in mind, because we will keep coming back to those in terms of the mitigation potential. Remember, here we are focused on solutions on bending the curve, which means reducing the total greenhouse gases in the atmosphere and reducing the warming rates, business as usual, and then bending the curve. So everything is a lot of complicated details that are going to be smoothed out here in some sense, because this is mostly a course that surveys all the methods and gives you a sense of the solutions, and they are not very region specific, even though the idea was developed in California. A lot of data is for California and the US, but we have tried to give it a global context wherever possible. So anywhere you want to apply these methods, like in India, one has to go specifically into the types of vegetation, type of climate. So we'll see that the soil organic carbon, for example, depends very much on the local climate. So we'll see global maps to see where soil organic carbons are high and where soil inorganic carbons are high. So any mitigation and management methods we consider have to be very region specific. Okay.